VLSos here. This is a video lesson on Newton's method. Have you ever wondered what the square root of 2 is? If you needed to approximate the square root of 2, you'd have to go to a calculator. The square root of 2 can't be written down exactly because it's irrational. Its decimal goes on and on forever without repeating. A calculator doesn't have in memory a table of values for irrationals. There's too many that the calculator would be asked to produce. The calculator goes through a process to approximate irrationals. And that process is something that we can do by hand using a calculus technique. We're going to be clever. We're going to say that the square root of 2 is equal to x. In other words, we're choosing x to be the value of the square root of 2 that we're trying to find or that we're trying to approximate. And in doing that, in assigning x to be the value that we're trying to find, we've also created an equation, which is going to be helpful because we can graph equations and get a visual idea of what we're trying to find. I'm going to modify this equation by squaring it, or squaring both sides, and then subtracting 2. I have an equation which is a parabola in standard form. Let's get a graph of that to visualize what we're talking about. I'm going to create space. I'm going to say that every 2 boxes on my graph paper is an interval of 1. This quadratic equation that we're graphing is y is equal to x squared minus 2. It's the parent parabola that has been moved down 2. So its vertex is here at 0, negative 2. And quickly graphing by creating some more points. I've got the quadratic graphed, and the original x value that we're trying to find, the approximation for the radical 2, is the x-intercept on this graph. If x represents radical 2, then I can find it on this graph by setting y is equal to 0 and observing where it crosses the x-axis. Where it crosses the x-axis, the x value of that point is radical 2. But how do I find an approximation for it? I'm going to start with an initial estimate. I'm going to say that x sub 1 is an estimate for the x value of this point. And I'm going to start with a crude estimate. I'm going to say that this parabola is crossing the x-axis at about 2. Now that is a very crude estimate because 2 is here. And I can see that there's a difference between where it crosses and my initial estimate. That difference is what we call the error. The error of my estimate is the difference between the actual value that I'm trying to find and the value that I'm approximating. But with this initial estimate, we can do something very clever. We're going to take advantage of the concept of linearization. Linearization is the idea that a line can approximate a curve. And a line is a better approximate of a curve closer to where the line intersects the curve. What do we mean by that? Well, we're going to draw and find the equation of a line tangent to this curve where the x value of the point of intersection is my crude estimate that I'm starting with. Visually, that means that I'm looking for a line tangent to the curve at this point. Why would I do that? Well, notice where if I project the tangent line down to the x-axis, that the tangent line's intercept is closer to the value that I'm trying to find than the estimate that I started with. In other words, linearization, the tangent line being an approximation of the curve, is going to produce an intercept which then is a better estimate. My crude estimate has an error which is the distance between it and the value I'm trying to find. And visually I can see that the tangent line is going to reduce error because its intercept is closer. So what I need to do to find this value, and I can because lines are easy to work with, is I need to find the equation of the tangent line and then use it to find that specific value. So what's the equation of the tangent line? Well, an equation of a tangent line requires a point of intersection. I have it. Its x value is 2. And its y value is found by putting this 2 into the original function. And when I do, I get 2 squared is 4 minus 2 has a y value of 2. So I have the coordinates of intersection. And I need the slope of that tangent line. The slope is going to be found by the derivative. The derivative of this equation here is 2x minus 0. So I will not include the minus 0. The slope of the tangent line is the derivative of the parabola evaluated at my initial crude estimate. If I put 2 into the derivative, I get a value of 4. The slope of the tangent line is 4. And the value of the function at 2 is 2. This is enough information to now get the equation of that tangent line. The equation of the tangent line is y minus the y value of the point is equal to the slope of the tangent line times x minus the x value of the point. I have the equation of the tangent line. And the reason I did it is because I want to know what the tangent line's intercept is. That intercept is the x value where the tangent line crosses the x-axis. And what is valuable about that is that it reduces the error and gives me a better estimate than my original estimate. So what I'm trying to find is the point of intersection here. And that's going to be the x value of my tangent line equation when y is equal to 0. So if I set y is equal to 0, I'm going to solve for x. I solve for x by dividing both sides by 4 and then adding 2. Negative 2 divided by 4 is negative 1/2. Negative 1/2 plus 2 is a positive 1.5, or 3/2. This 3/2 is a better estimate than my original estimate of 2. And because it's a better estimate, it's traditional to put, if I chose x sub 1 to represent a cruder estimate, then the better one would be x sub 2. 1.5 ought to intuitively be seen to be a better estimate of radical 2. But I could use this new estimate of 1.5 to get an even better estimate by repeating this process. That process is, at the better estimate, finding the value of the function, drawing a tangent line to that function whose x-intercept is even closer to the value that I'm trying to find because it reduces error. So to find that intercept, I would find the equation of my new tangent line, set y equal to 0, and solve for the x value or the x variable of that tangent line to get a better estimate. And I can continue to improve my estimate, which would then improve the approximation of the actual x value or the intercept of the parabola. I would never get there because I can never get exactly the value of an irrational. I can just improve my approximation. In general, this process is the process of finding tangent lines to a curve and solving for x. So in general, the tangent to a curve is y minus a y value, which comes from putting into the function an estimate. In this case, we'll say x sub 1 represents an initial crude estimate. Then continuing is equal to the slope of the tangent line, which is the derivative of the function evaluated at the initial crude estimate, or symbolically f prime evaluated at x sub 1, times x minus the x value of your initial crude estimate. But remember, this is the equation of the tangent line. What we're looking for is to improve our estimate. And that means that we're looking to solve for that x. This would be the improved estimate. And if we wanted to solve for this x, and that x represents an intercept, then our y value is 0. And we can get x by itself by dividing both sides by f prime evaluated at x sub 1 and then adding x sub 1. In other words, I can get the better estimate, this x, by taking this side, negative f evaluated at my original estimate, and dividing by the derivative, f prime evaluated at the estimate, and then adding the estimate. And if the notation x sub 1 was used for the older estimate, then the improved estimate would be x sub 2. Or, in even more general terms, you can repeat this process indefinitely to improve estimates. In this case, we'll call it x sub n plus 1, a one more improved estimate over x sub n, and it will be equal to, starting with the cruder estimate x sub n and adding, or in this case adding a negative we could turn into subtraction, the value of the function at that estimate divided by the derivative of the function evaluated at that estimate. In most general terms, this is a process that you could continue to repeat to improve your approximations of rational functions. And this here, this formula to improve estimates, is called Newton's method. And it is a fantastic and helpful way to get values from things that we couldn't previously evaluate.